Bismillahirrahmanirrahim. This video will be discussing third order Butterworth filter with Sallen-Key implementation, and along with we'll be discussing example 16.15. And for this a student has requested. Let's proceed. The first question that comes to many students' mind, and also in my mind it came, what is the difference between Butterworth and Sallen-Key filters? Actually, the key difference is that the Butterworth refers to a filter response type, maximally flat magnitude response. So the Butterworth response would be something like this for a low pass filter, almost straight, and then sharply falls to zero level. And what is Sallen-Key? Well, Sallen-Key refers to a circuit topology or circuit diagram, practical operational AMP based implementation, just like shown here. So this is the Butterworth filter behavior or the output wave, and this will implement this Butterworth. Sallen-Key will implement the design. So in short, we can say that Butterworth defines what the frequency response looks like, and the Sallen-Key defines how to build it. Little more theoretical part. When we talk of the higher order filter, let's start with, let's say, second order low pass filter. Then we can just connect or cascade two first order low pass filters to make a higher order or a second order filter, similarly 3, 4, etc. And if you recall, the transfer function for the first filter will be like this. I'll not go into the details. You can check from the book. Not really important, just to give you an idea. The same with the second one. And the combination will have the multiplication of the two to get the transfer function, complete transfer function, and which will look something like this. And to improve upon this basic approach, we go for the Sallen-Key filter. We were here, and as we said that we can use Sallen-Key filter, which is improved version. So this is the design of the filter. Sallen and Key, they designed this filter. This is also a second order filter. And if keep this filter in mind, this is a non-inverting filter. You can see the output is, sorry, the input is going to the positive terminal, so non-inverting. And we know that the relation between output and input is like this. So if you bring it here, this will be the gain. So gain in this case, instead of RF and R1, we have RA and RB. So the gain for this filter can be written as RA plus RB divided by RB. This is our equation number 37 in the book. Now, this has been derived in one of my previous video. I'll not go into the details, but the transfer function for this filter will look like this as shown here. You can also see the book. This is how it has been derived in the book. And now for simplification, what we are going to do is remove R1, C1, R2, C2 and just make them R. So R1, R2 will be calling R, C1, C2 will be calling C. And so this will further simplify 1 over RC. This will also be 1 over RC and like this. So this is a further simplified version. So we were here, and now we can take LCM for this item, and the inside the big bracket it will be then 3 minus G RC, and remaining this will be R square C square S. Now, if we from the book, if we find the general definition or general filter transfer function of an nth order Butterworth filter, the BW Butterworth, so it will be as shown here. We are mainly concerned with the denominator. And for second order, we'll just put n is equal to 2 in this equation. So the denominator will be s square plus a1s and plus a0. So we were here. This was the Sallen-Key equation simplified. And this is the Butterworth equation for the second order filter. Now all we need to do is just compare this. A1 is this thing and A0 is this. So matching to Butterworth from Sallen-Key to normalized Butterworth filter. A0 is 1 over RC square. This is our equation 41. And A1 is 3 minus G over RC. This is equation 42. So must for a Sallen-Key filter to be Butterworth is this condition, and especially this is very important. We'll be talking about this. Now the question that we'll be solving in example 16.15 deals with a third order Butterworth filter or third order filter. So we have to keep that in mind. Now, as we had discussed that, this was the general equation. So for third order now, we'll put n is equal to 3. So this will be the third order filter equation for Butterworth. And now we use this table 16.2, and from here we can get the coefficients for the low pass Butterworth filter. This is third order. So A0 will be 1, A1 will be 2, A2 will be 2. And remember that this is for the case when the cutoff frequency has normalized to 1 radians per second. So if we put these values now in this equation, so the third order filter denominator will now be s square. A2 from here you can see is 2, so 2s square. And A1 is also 2, so 2s plus 1. Okay, so we were here. Now we need to have, we know that the Sallen-Key filter is a second order filter. So we can just break it down in a manner that we can have a separate filter whose pole will be at 1, or s is equal to minus 1. S plus 1 should be one factor, and the other factor we can get from here is just by dividing. We're dividing this by s plus 1. So this will be the denominator for the Sallen-Key. So this will be our equation. And as you can see, Sallen-Key will generate this part, and this filter, another inverting filter or inverting op-amp circuit will be generating S plus 1. How to go about? See, if you see the first order low pass filter, inverting filter, this we can solve to get its transfer function. Not go into the details, but you can just follow these steps. So this will be the transfer function. And from here, we know if we put the denominator equal to 0, we get the pole. So this will represent pole. So just like here, S plus 1, we have S plus this term. And we have known that for the second order filter, this is the denominator, and we had also derived that the for Butterworth, Sallen-Key to be Butterworth implementation, this is the relation. And if we just for ease, we write it A2 S square, then A1. This is the general equation. Then from here, we can find that A2 we don't need. We need is A1 and A0. So A1 is 1 from here, and A0 is 1 from here. So the first case we put 1 for A0, and the second case we put 1 for A1. So this is the Sallen-Key implementation. Now we have plugged in the value of A0 and A1. That means from here, RC should be equal to 1. And from here, 1 minus 3 over G, RC is equal to 1. And that means G has to be 2. Now, this is very important. Keep in mind, so the gain of the second order Sallen-Key or the Butterworth implementation should be equal to 2. Now, let's come to the question. Design a third order low pass Butterworth filter having a gain of 4 and corner frequency of 2000 radians per second. First of all, let's begin by selecting the Sallen-Key prototype shown in figure 1648. So this is the 1648. We have to now find the values of different components. For the purpose of simplification, as we discussed already earlier, that C1, C2 will be called C, R1, R2 will be called R. So this will be the simplified form. And now the first part, we had written it like this. From here, we mentioned we're getting another pole. So 2 poles from here and 1 here. So it will be 3 pole circuit or third order circuit. So adding these two, now this will be our complete circuit. Now this gain of the first stage, if we call it G1, and then gain of the second stage we call G2. Gain of the second stage is controlled by RA and RB. This is a non-inverting amplifier. Also, this resistor and capacitance, they control the frequency, corner frequency or cutoff frequency. So now we have two options. Our question says that we have to have a gain of 4. Option is that we take gain of the first part as 1 and gain of the second part as 4. That is one possibility. The other, we can say that gain of second part is 2 and also the gain of first part is 2. So that is another possibility. So the gain of this Sallen-Key Butterworth implementation should be equal to 2. Now we have already discussed in the previous slide that Sallen-Key to be a Butterworth implementation, the gain has to be 2. But the book has taken it to be 4. Don't know the reason. But the preferable method is that we take this option, 2 of the first stage and 2 gain of the second stage. But anyway, to keep pace with the book, we'll follow the book method and then we'll discuss the second option. But this is inconsistent with what we have found out. So now we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order filter. So we have to find the gain of the second order fil So what we're going to do is take gain 1 here of the first stage and gain 4 of the second stage. So RC is 1 and G or the gain is 4. So putting RC is equal to 1. Here we get RC is equal to 1 from this relation. And this gain can be found from here. Instead of RF and R1, we have RA and RB. So for 4, this is 1. So this part must give us 3. That means G is this relation we have already talked. Now if we assume RA to be 3 kilo, then RB has to be 1 kilo from here. 4, then this is 3 kilo, and you can calculate RB to be 1 kilo. Now we go for the capacitors and resistance which control the frequency. Initially, we designed for R is equal to 1 ohm and C is equal to 1 farad, and this will automatically satisfy RC is equal to 1 requirement, or the frequency to be 1 radians per second. But we have to actually design it for 2000 radians per second. So there comes the scaling factor. Omega C is this. We have calculated or we have used these values for omega C is equal to 1. R1 and C1, either value being easy to locate. So if you go into the market and try to find, this would be very difficult. So we'll use the standard value. So we'll select more reasonable capacitor value, which is 0.1 microfarad. And let's call it C double dash. And assuming the cutoff frequency 1 earlier, now that we want it to be 2000, we will get a scaling factor which is known as Kf to be 2000. And this formula is given in the book. I have also explained in one of my videos for example 1614. These are for the magnitude scaling. This is for the frequency scaling. And this is for when we are doing both frequency and magnitude. In this case, we will be using this formula because we are doing the magnitude and frequency both. From here, we'll find Km factor. The Km factor is the factor which is used to find the new resistance value. This Km we need to find from this relation. So C double dash is C over Km Kf. From here, Km will be C divided by C double dash Kf. C is the initial value of 1 farad, and C double dash is the new value that we have selected, and Kf is 2000. So from here, Km is 5000. So new R double dash, I'm calling it Km into R, 5000 into 1 ohm is 5 kilo ohm. Okay. So now we'll plug in all the values. This we have found to be 3K. This is 1K. Capacitor 0.1 microfarad we had taken, and the resistance 5K. So this is should be able to get us a gain of 4. Now we need to find the values of the first stage. This is the transfer function of the first stage. This is an inverting amplifier, so negative sign. And from here, we can locate the pole. From here, putting equal to 0, this will be our pole. The pole location sets the corner frequency or the cutoff frequency of this specific stage. So this will be the cutoff frequency of first stage. From here, we just take 1 over RFCF. Now, if we initially take RF is 1 and CF is 1 farad, as we had done it in this case, then here also we can find the cutoff frequency to be 1 radian, which was here initially. For this, we had also taken the cutoff frequency to be 1 radian. And now we'll convert into 2000 radian. So exactly same technique. Recall that for Butterworth also we had assumed normalized cutoff frequency to be 1 radian. So this is also same. So we'll use the same scaling technique. So omega C1 new now has to be 2000 radians to match with this. So this is operating now at 2000 radians. So this has to operate the same frequency. And for this exactly same technique, 1, we select 0.1 microfarad. We find Kf and then we find Km. From here, then Km and then R will be 5000 multiplied by 1, so 5K. So 5K here and 0.1 microfarad here. The only thing remaining is R1. Now remember, this sets the frequency, not the amplitude. To determine R1 for gain requirement, we want the gain of the first stage to be 1. The gain of an inverting filter is actually negative RF over R1. But since we are only taking magnitude, it will be RF over R1. So it has to be 1 because that is what we want. Now RF we already know is 5. Therefore R1 has to be 5 to get a gain of 1. So RF 5, therefore R1 has to be 5K. So this completes our design to get a gain 1 from the first stage and 4 from the last stage. But as we had some reservation, I took help of DeepSeek also, and the recommendation is that the book's G is equal to 4 choice with their assumptions leads to unstable Butterworth design. For a stable Butterworth filter, G must be less than 3. So G has to be less than 3, not 4. That is what DeepSeek is recommending. So let's go for the second option then. We want G2 or the gain 2 in the first stage and gain 2 in the second stage. So nothing new, exactly same technique that we have been following, but the frequency is not changing. Just this value will determine the gain here, and here also it is RF, R1 will determine the gain. So the gain of the second stage, and from here it is 2, 1 plus RB2. And from here, we can see that RB has to be equal to RA, and we can take any value in kilo. If we take 1 kilo RA, then RB has to be 1 kilo. 1 kilo, 1 kilo. The capacitor resistance, which determines the frequency, will remain unchanged as we had calculated in the previous section. Same way. And the RFCF value will also remain same as it calculated earlier. So here also we'll have only the RF is 5. Therefore, R1 has to be now 2. The relation cannot be 1. Here G is 2. RF over R1 has to be 2. RF is 5K. Therefore, R1 has to be 2.5K. I hope you have been able to follow this. Please let me know through your comments. Thank you.